All right, we'll go ahead and get into this next section of notes here. So today we're getting into 8.3, and we're actually combining a few of the different lessons from the textbook here. We were talking about inscribed angles, and we were talking about tangents. And tangent's going to be a little bit different than what we've seen before. If you remember, we discussed that earlier with trig functions when we had sine, cosine, and tangent. This is also going to be tangent, but it's going to be used in a different way. It is not the same thing as the function that we've discussed. Okay, so today is the 6th. If you'd like to add that, our objective for today is we want to be able to find angle measures, arc measures, and line segments or side lengths given tangent lines with circles. Okay, so first off here, first thing we need to talk about is what's called an inscribed angle. So we've talked about a few different types of angles that we see with circles here. This next one is what we call an inscribed angle. An inscribed angle is this. It is an angle inside a circle, whose vertex lies on the edge of a circle, or the circle, I should say. Okay, an inscribed angle is an angle inside a circle whose vertex lies on the edge of the circle. So for example here, what this will usually look like, right here we could draw a circle, okay, and like we said, we just need to really pick a point and create an angle from it. So for example, let's say we took this point here and we created an angle here, okay, this would be what we call an inscribed angle, this part right here, okay, and so we have this, and then we have another piece that kind of goes along with it, which is what's called the intercepted arc theorem, okay, the intercepted arc, or not even the theorem yet, but just intercepted arc. And an intercepted arc is just, and let's see, make sure I have some room here. An arc whose endpoints, okay, an arc whose endpoints are part of an inscribed angle. Okay. An intercepted arc is just an arc whose endpoints are part of an inscribed angle. So for example, this piece right here is what we call the inscribed angle, and then this piece, this arc that we have right here, is what we'd call the intercepted arc. Okay, so we have two different things that we can see there, and this is helpful because we have a relationship between this angle in the middle or inside the triangle, or inside the circle, excuse me, and the arc on the outside. Okay, and this is what we call the inscribed angle theorem. Okay, so the inscribed angle theorem says this. It says the measure, we'll say this, we'll say the measure, or we'll say in a circle, whoa, things are moving around here. The measure of an inscribed angle, will always be half the measure of the intercepted arc. Okay, in a circle, the measure of an inscribed angle is always going to be exactly 1/2 of an intercepted arc. Okay, so for example here, if we're using this picture that we drew earlier here, we could just keep it simple. We could just say angle, or we could say point A, B, and C here. So notice the inscribed angle, we could just call A, and then the intercepted arc is arc BC. And so what I would say here is I would say, sorry, this keeps kind of moving on me here. We'd say the measure of angle A is always going to be 1/2 the measure of arc BC. Okay, this is what the theorem is telling us here. Okay, so this is nice because now I just know if I have one of them, I can find the other. Okay, so A is half of the arc of arc BC, or in other words, if we want to swap that around the other way, arc BC is always going to be twice the size of angle A. Okay, either way we can use that here. Okay, so first off here, example 1, let's say we're given this circle and we want to find each of these measures here. So first one I want to find, if I'm looking at this, is finding the measure of arc PO here. So I'll go ahead and draw this in. Okay, draw this in here. And if we want to find this, we're going to use that theorem that we talked about. We see that the angle that created this arc was 56 degrees. Okay, so if I needed to, I could really kind of just set up an equation. I could say angle N, okay, if we're using what we just talked about, I could say the measure of angle N equals 1/2 the measure of arc PO. Okay, if I'm just using that exact theorem that we just wrote down, this is what I would say. Okay, or in other words, if we want to swap this around, like I just mentioned, we can say if I double or multiply the measure of angle N by 2, that's going to equal the measure of arc PO here. Okay, either way will get you to the same answer here. Okay, so in any case, we know the measure of angle N, so I'm just going to say this equals the measure of arc PO, and it is 2 times the measure of angle N, which we see right there is 56. So all I need to do is 2 times 56. So my final answer here, I'll go ahead and write this out to the side. Measure of arc PO equals 112 degrees. Okay, so I know a lot of writing there, but just making sure we understand the concept. PO is just double the size. Okay, and then another one here, we have angle P now. So if I just look at this angle here, measure of angle P right there, go ahead and erase everything else. I notice with this angle, it created this intercepted arc of 70 degrees. Okay, so if that's the case, we could set up the same kind of equation. We could say the measure of angle P is always going to equal 1/2 of that arc that is outside of it, which would be arc MN in this case. Okay, so in other words, we can just plug that in here. Measure of angle P just equals 1/2 of 70, or in other words, 35. Okay, 35 degrees. Okay, so pretty straightforward. On these kinds of problems, you're always either cutting something in half or you're multiplying it by 2. It just depends on which angle or which measure you need to find. Okay, so that's one thing that we know with arcs and the angles inside. And then we also have one other theorem that kind of goes along with this, which is what we call the intersected arc theorem. Okay, and the intersected arc theorem says this. It says if two intercepted arcs have the same endpoints, okay, if two intercepted arcs have the same endpoints, then what we can say is then their inscribed angles are congruent. Okay, if I see this is the case where there's two arcs in the same circle and they have the exact same endpoints, what that means is the angles across from them are going to have to be congruent as well. Okay, which makes sense because both those angles would have to follow that other theorem that we just wrote down. Okay, so again, for example here, try to draw this out here. Try to give myself as much space as I can. Let's say we have one inscribed angle here. We'll draw it like this, here and here. And then let's say, and then we'll call this, we'll just label this A, B, and C. Okay, keep it simple. And let's say we have another arc that has the exact same endpoint. So let's go here and then here. Okay, so still ends at A, still ends at C, but instead this one is angle D here. Okay, what I would say here is I would say the measure of angle B is going to have to equal the measure of angle D. Okay, and like I said, that kind of makes sense because both of those, I don't need to circle that, but both of those are going to have the exact same arc that they're across from, so whatever that measure is, they're going to have to be half of it, which is going to be the same number. Okay? All right, so example 2 here, practicing this a little bit. Let's say we're looking at this kind of circle here, and we see a similar kind of picture to the one that we just drew. Okay, I see that I have two arcs. I have, or this angle right here, angle T, and angle U, and they both have the endpoints of SV. So what does that mean about them? It means that angle T and angle U are going to be congruent. So if I want to solve for x here to start, I just need to set these equal to each other. So all I'm going to say is I'm going to say 3x minus 5 equals 2x plus 15. And then do the algebra. Subtract 2x. I do that. Oops. I don't want to cancel those out. These cancel out. I'm left with x minus 5 equals 15. So add 5 to both sides. And we get x equals 20 here. Okay, so x equals 20, and then always a good habit in this class, double check. Do I need to plug that back in? In this case I do because it's asking for the measure of angle T. So I would say t, measure of angle t equals, and we're going to plug this back into 3x minus 5, so 3 times 20 minus 5. So we'll say the measure of angle t equals 3 times 20, which is 60, minus 5, and so this is going to be 55 here, okay? And if we really wanted to, we could be specific. We could say 55 degrees, okay? But this is the idea, and you'll see a lot of problems like this on our homework where it's pretty much on these, you're just kind of setting them equal to each other because they both have the same arc, okay? So nothing too complicated so far, just talking about cutting stuff in half, doubling things, finding the measure of these different angles, okay? Other things that we need to talk about for today, other than inscribed angles, is what we call the tangent to a circle. Tangent to a circle, okay? A tangent, in this context, is a line that intersects a circle, okay, a line that intersects a circle in exactly, or I should say at exactly, 1 point. Okay, a tangent is a line that intersects a circle at exactly 1 point. So, for example, if I'm sketching a circle here, try to draw this a little bit smaller so we have some room to write in the rest of our explanations here. What I would need is I would just need a line that crosses this circle, but it has to touch it at exactly 1 point. So notice if I kind of draw a line here, it crosses the circle multiple times. So I need this pretty much to just go right along the edge and just kind of intersect 1 point, okay? And so this is what we call, and I'm going to label this as well, okay? The point where they intersect, that is what we call the point of tangency. Okay, intersects it at exactly 1 point, no more, no less, okay? And then this leads us to the tangent theorem, okay, something that we know about tangents, and we can say this, we can say a line is tangent to a circle, okay, a line is tangent to a circle if and only if it is, okay, a line is tangent to a circle if and only if it is perpendicular, okay, perpendicular, let's fix that here, to a radius drawn to the point of tangency. Okay, kind of a long, wordy theorem here, but, okay, we'll kind of talk through what it means. Okay, a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. And so we've seen that phrase before. If and only if means it works both ways, okay, or it has to work both ways. So for example, if I'm looking at this picture that we drew before, and I see this right here, what this would mean is if I drew the radius from this point to the center, these two lines here, the tangent line and the radius, would have to be perpendicular. Or in other words, they would have to intersect at a 90-degree angle. Okay, so it just gives us more information and ways that we can use that angle here. And you can kind of guess how we're going to use that. We've seen this in the past few lessons. When we see the word perpendicular or we're talking about a right angle, usually we're going to throw in a right triangle in there somewhere, or use all that information that we talked about in trigonometry. Okay, so example 3. Let's say we're looking at this one here. We're told from the very beginning that JH is tangent to the circle at J, which is good. We need to be told that from the start because we can't just guess. And we want to find the value of X here. So if I'm looking at this, first off, if we're just using what we talked about, if JH is tangent to the circle here at this point, like we just said, we know those two lines, the radius and the tangent line, are going to be perpendicular. And so now if we look at this, this means I have a right triangle. And if I want to set up an equation to solve for X, I need to use what we've talked about a bunch in the past, which is the Pythagorean theorem. So to set this up here, we do a squared plus b squared equals c squared. So I would say x squared plus 12 squared equals, and to represent the hypotenuse here, I don't want just x or just 8, but I want those added together. So I'm going to say x plus 8 all together in parentheses and then squared. Okay, so x squared plus 12 squared equals x plus 8 squared. Okay, and now we need to solve here. So x squared is not going to change for right now. 12 squared we should know, that's just 144. And then here, when we get to x plus 8 squared, we saw this on a homework problem earlier in the semester. Remember, we can't just distribute the square to both those terms. This is not the same thing as x squared plus 64, for example. What we need to do is we need to write this out as x plus 8 times itself. So x plus 8 times x plus 8. And we talked about a way to do that. We can use what's called the box method here. And there are other ways to do this as well. Okay, either strategy you use is fine as long as it gets you to the correct answer here. And I would set up a box with x plus 8 and x plus 8. And now every box is just going to be the product of the length times the width. So top left box here is x times x, that's x squared. Top right box is going to be 8 times x, or 8x. Same thing with the bottom left, that's 8x. And then the bottom right, 8 times 8 is 64. Okay, so I have this here, and I could just write this all out. X squared plus 8x plus 8x plus 64. Okay, or in other words here, we'll simplify this on the next step. Okay, I can combine my like terms. 8x and 8x add together 16x, so this is x squared plus 16x plus 64. Okay, and we haven't talked a lot about how to solve an equation when you have an x squared in there. And so the good news here is we're not going to have to deal with that because I have an x squared on both sides of the equation. So what I would do is I would just subtract those out, so I don't have to worry about that. Okay, on the left side they cancel, on the right side they cancel. So really I just have a simpler equation now. 144 equals 16x plus 64. And now solve from here. This is just algebra that we've done a bunch. Subtract 64. Okay, when I do that here, those cancel. I get 144 minus 64, that's just 80. And then equals 16x. And last step, divide by 16. And we get x equals 5 here. Okay, and so this is our final answer here. X equals 5. This is all it was asking us to find. If we needed to, we could plug these back in and double check, make sure they work. In that case, they would. Okay, so that is how we use tangent lines. And then one more thing that we have here as well, similar kind of concept to what we talked about with intercepted arcs actually. It's not too bad. It's just called what we could call the two tangents theorem. And we can say this. We can say if two lines are tangent to a circle, and we'll say to the same circle. Okay, if two lines are tangent to the same circle and have, or we'll say and share the same exterior point, then what I can say is I can say they are congruent. Or in other words, they are the same length. Okay, if two lines are tangents to the same circle and they share the same exterior point, then they are going to be congruent to each other. Okay, so we could draw an example with this, but we'll see this on example 4 here. So we'll just use this as the example to kind of look off of here. Okay, so let's look at this picture from example 4. And so this is describing the theorem that we just wrote down. I have two lines that are both tangent to the circle. Okay, I know they're tangent because it tells me wx and xy are tangent. And they have the same exterior point. They both kind of come together at the same point, which is x. Okay, and all it's saying is it's saying if this is the case, then what I need to do is I need to find x and then find the length of wx here. So if I'm going to set up an equation like we just talked about, if I have two lines that look like this, what that means is they're going to have to be congruent because they share the same exterior point. So all I need to do is I need to say 2x plus 9 equals 3x plus 6. And then solve from here. We can do a few different things. I'll go ahead and subtract 2x first. Usually like to deal with the variables first, so I cancel. We get 9 equals x plus 6. So last step here, just subtract 6. And we get x equals 3 here, or 3 equals x, depending on how you look at it. Okay, so x equals 3 here. Always good to double check. Do I need to plug this back in? In this case, I do. I need to find the length of wx. So I'm going to say wx equals 2 times 3 plus 9, because I'm just using what we were told wx, 2x plus 9 here. So wx equals 2 times 3, which is 6, plus 9, so wx equals 15. Okay, and like I said, similar kind of problem to what we've seen on the earlier in this notes, and then also just in general, just what we've done a bunch in geometry, setting two things equal to each other, finding the variable, and then plugging it back in. Okay, so make sure you use these theorems and just use these examples while you're working on your homework here. Homework for this is going to be 11.3, and as always, that'll be posted on the class website. Okay, if you guys have any questions, feel free to let me know. All right, thanks guys.